So the presentation we are presenting is applying diffusion models for medical image anomaly detection. So our team is Umar, Khalid, and Kasun. So the content-wise of this presentation, we're gonna talk about problem and motivation, related work, proposed work, method, and experiments, and then the future directions. So the problem definition, we know that medical applications require anomaly detection, weakly supervised methods, only image level annotations are required, no pixel labels are required. The current methods that that has a great interest is generated adversarial networks and autoencoders. The limitations of these methods are complicated training, and then we know that generated adversarial networks, they're having difficulty to find details because they do not preserve the fine details. So we have these limitations. To address these limitations, so we have a motivation. We investigate the diffusion-based generative models, denoising diffusion implicit models, in other words, DTIM-based approach. So objective is pixel-wise anomaly detection. Technique we use is image-to-image translation. So the guidance control classifier guidance. So here in this method, no pixel-wise labels, so which overcome one of our major limitations. And then this is simple. And the last one is quality anomaly mapping, because most importantly, because in medical image, this is one of the critical area. So now we have to do the literature survey. So the Umar.
Yes. So as Kasun has mentioned, like the thing that we are trying to investigate is to see how through weak supervision we can achieve good anomaly detection for medical images. So for that, the first figure you see on the top is primarily discussing the diffusion approach, where we add a noise to an image, Gaussian noise. And the second image that you see is basically explain how we denoise the sample. The approach over here is basically from a paper, DTPM, this figure, which mentions is that, which uses Markov chain, Monte Carlo sampling, that the future state is dependent on the current state, or we need the information for current state to generate the next state. And basically, it consists of any diffusion method consists of two stages, noising and denoising. There is a slight modification to this method. Next slide, please. So there's another approach presented by another paper, DDIM, where basically they try to modify the typical diffusion denoising process and replace it with non-Markovian, where the sample at time t is also dependent on x0, which is a clean sample. So in this way, we can generalize the forward diffusion process by using non-Markov chains. And the key objective and the key idea of this paper is that basically instead of approximating xt to xt minus 1, we approximate epsilon using x0. Training objective is same as GTPM, but the diffusion process can be slightly faster because we do not have to use a predefined number of steps that we have been using in DTPM. So keeping these two papers in mind, basically, next, we try to investigate what other papers have used it. So another paper, Glide, is basically used image generation using clip models, and they use and apply the control through a text prompt. Another paper which uses DDIM-based methodology is basically stable diffusion. They also use this text-based control, but they do add noise and denoising in the latent space instead of the images. So we have a kind of encoder through which we convert an input sample X into an embedding, and that embedding, and then at that embedding, we add the noise. And we denoise the same embedding using a control signal, which in case of latent diffusion paper is basically a text prompt. And then we can have a decoder to get original picture X, which is conditioned on our prompt. So using all these ideas from latent diffusion, from DDIM, from DDPM, we come up with our own approach. Next slide, please. In which basically we will be using two unpaired sets of images. One image, one class will be basically the healthy images, and the second class will be diseases, will have diseases on them. And then we will be using their labels during our training as a condition. That is why we say it's a classifier-based guidance. It looks similar to stable diffusion, but instead of text prompts, we will be basically providing our guidance through a classifier. So during training, we will be using, during training, we basically will be using the original labels of healthy or diseased, but at inference, we will not be using a disease label. So what will happen, we'll pass only one label, for example, 0, which is corresponding to a healthy image. That is why even if at the input, the image is basically disease, have a disease in it, but after generation, what will happen that we will get a clean image. And based on this input and generated image, we can calculate the anomaly map, which is actually the difference between the original and synthetic image. And how we will do that, basically, we'll show you in the next slide. Here you can see a typical diffusion process if I apply that in a particular image. Passenger stop, please. So what happens if we have an input image and we are passing it to L steps, we have this encoded noisy image, and then we can have denoising and we can get an output where you can see in the output, we don't have that tumor highlighted. We don't see that tumor in the output. How did we achieve that? Basically, we pass that control, which will convert this signal, this image, image into a clean image. And then calculating this difference between input and output, we can get the anomaly map. So here you can see in the diagram, we inserted a cross. Why? Because we want to implement a concept from stable diffusion that we want to add a noise in the latent space. So we don't want to add noise in the original image. Next. So you can see we can pass that input through an encoder, which will give us an embedding. And on that embedding, we can have adding this diffusion process or adding noise. And after adding noise, we can get this noisy sample XT, which you can see as green here. So this is part one, step one. And then taking this noisy sample, then we can have this denoising diffusion process as was discussed in the previous slide of stable diffusion. Here, we can pass a control through our labels. During training, we can have 0 and 1 as original labels, and we want to generate the original image during training. And after decoder, we can have the original sample. But as you can see here, this input, can you go back? Go back. Yes, as you can see, the image at the output is different from the image that you see. Kasam, can you go next, please? Yes, it is different from the image on the top. This is because this stage I mentioned is because of the training. But at inference, what will happen? We get the clean image. How? Because at inference, we will only pass the label 0. Can you go next? Yes. So if we just pass a label 0, we can get a clean image. That clean image at inference is different from the input image. And based on that, we can get this anomaly map. Can you go next? So experimentation, basically, we are using two data sets, Brad's 2020 and Checkspert data set. And for, can you go next? Yes. And we are comparing our method with fixed point GAN and VA, variational autoencoder. And the evaluation matrices that we are using are basically dice score and AUROC. So that till this point, what we have done is basically we have tried to use a pre-trained diffusion model, stable diffusion, and we tried to evaluate it on first fine-tune it on chess expert. But our results were not good primarily because I think chess expert is relatively smaller data set from BRAS 2020. So at this stage, what we are trying to do is basically we are first trying to train the stable diffusion end to end on BRAS 2020. And then we will evaluate it not only on BRAS 2020, but also on Chess Expert. So we have implemented, but we are still in the process of generating the results. That's all.